Hello everyone, welcome to the session on the factors that affect the band position and intensity of electronic spectral band. So electronic spectra arises due to the transition in electronic energy level. This happens when we irradiate the molecule with ultraviolet or visible radiation. There are some factors that affects the band position and intensity. So they are listed over here. So the first one is the conjugation. Solvent also affects the band position and intensity. Next comes steric hindrance. pH also affects the band position and intensity. Let us see them in detail one by one. So first, when we look at the effect of conjugation, as the conjugation increases, the lambda max value also increases. Lambda max increases in the sense it is shifted to higher wavelength side. That means red shift, also called as bathochromic shift. Hope you remember about bathochromic shift. So let us take an example of ethylene molecule. So let us consider the pi bond formation of ethylene molecule. So this molecular diagram depicts the formation of pi bond in ethylene molecule. So ethylene has an unpaired electron on pz orbital, so that undergoes sideways overlap and results in the formation of pi bonding orbital as well as the anti-bonding orbital, that is pi star. Bonding orbital arises by the overlap of p orbitals, that is p plus p results in the formation of bonding molecular orbital, that is pi molecular orbital. P minus p results in the formation of pi star molecular orbital, that is anti-bonding molecular orbital. So when we irradiate the molecule with ethylene, the ethylene molecule by ultraviolet or visible radiation, then the transition occurs from bonding molecular orbital to anti-bonding molecular orbital, because the bonding molecular orbital, that is the HOMO, highest occupied molecular orbital. So the energy required for the system is delta E. So the energy required for transition is delta E. Now consider the formation of 1,3-butadiene. So 1,3-butadiene is formed by the combination of two ethylene units. So hence I have given the same molecular orbital diagram of ethylene molecule here. So this is the molecular orbital of ethylene moiety. I have also given the same thing in the right hand side. So this is the molecular orbital of another ethylene moiety. So these two combines and results in the formation of 1,3-butadiene. So these pi orbitals combines together, that is pi plus pi results in the formation of Xi1. That is the first molecular orbital of 1,3-butadiene. Here complete overlap occurs. So the molecular orbital Xi1 doesn't have any nodes in it. So the next one is pi minus pi results the formation of Xi2. So just the pi of one ethylene moiety and pi of another moiety. So just changes its sign and combines. So it results in one nodal plane in the orbital. So next one is Xi3 molecular orbital, that occurs by pi star plus pi star combination. So this results in Xi3. Xi3 has two nodal planes. So Xi3 has two nodal planes in it. So next comes pi star minus pi star. So that results in the formation of Xi4. So 1,3-butadiene has 4 molecular orbitals, Xi1, Xi2, Xi3 and Xi4. So Xi4 has 3 nodes in it. So this is the molecular orbital diagram for 1,3-butadiene. So here each ethylene has 2 electrons, overall 4 electrons. So after filling up it in the molecular orbitals, so Xi1 and Xi2, so that here the HOMO is Xi2 level. So Xi2 is the HOMO, highest occupied molecular orbital. So when we irradiate 1,3-butadiene with ultraviolet radiation, so excitation happens from HOMO to LUMO. So the transition occurs from Xi2 to Xi3. So the energy required for this transition is a delta E. As we compare it with the energy required in the case of ethylene, this is much more lesser. Since delta E is less, you also know the relation between E and lambda. So they are inversely related. Since delta E is less, lambda max will be more. That means it leads to the change in wavelength to higher wavelength side. So that is bathochromic shift. So as the conjugation increases, the lambda max also increases.